Hello, we've been lately talking about amplitude modulated sensors, and in the last lecture we were talking about one example of an amplitude modulated sensor. We went into an example a little more detail, which is based on absorption spectroscopy. And we saw as part of absorption spectroscopy that we could one of the applications of absorption spectroscopy is for picking up absorption lines of gases, trace level of gases. And so we looked at an example of how we can send light in through a gas cell which has got a particular concentration of a particular gas species, and the idea is how do you determine that concentration. So then we looked at how we can do these measurements, especially with differential absorption spectroscopy, how we can get an accurate measurement of the gas concentration. So that part is great, but if you observe closely, this gas concentration is not going to change over a period of time, right? So you can actually make this relatively static. You can call this a relatively static measurement. Okay, so you can certainly employ different techniques to improve the signal to noise ratio of the measurement, and of course you can do averaging as well. But we thought what we discussed previously was if you could do lock-in detection, we could possibly get to a very, very low level of detection. So we can really bring down the detection limit as far as our measurement is concerned. And while I was talking about lock-in detection, I casually mentioned that we may want to do this at kilohertz frequencies, like 10 kilohertz frequencies and so on. So I'm referring to the discussion that we were having here, where I was saying that we may want to modulate the source at a particular frequency, and that could be in the order of 10 kilohertz. But I did not tell you why we are actually doing this, why we want to do at such a high frequency. Okay, so of course we do need a frequency carrier so that we can lock into that frequency carrier, and then we can lock into the phase and achieve fairly good signal to noise, or improve your signal to noise ratio. But one of the reasons why we want to go to higher frequencies is because of the fact that there exists a type of noise at lower frequencies, which is called the 1/f noise. As the term itself implies, the noise amplitude or the noise power actually goes down as a function of frequency. So it's predominantly available only at the lower frequency, and this 1/f noise is also called the pink noise, or it's also sometimes called the flicker noise. Okay, it's something that I think we're familiar with the Johnson noise. The Johnson noise is something is other name for thermal noise, but that's named after this person Johnson. And when Johnson was actually making these measurements, he noticed that there is this 1/f type noise at low frequencies that he was not able to actually comprehend what it was. But he was the first one to report such noise, and that was subsequently termed as flicker noise. Okay, the origin of this noise is still being debated. So there are different sort of explanations for this noise, but what we are actually considering it as is it's electronic noise, because it's actually showing up in our receiver electronics, and what it may be due to as far as receiver electronics are concerned, it could be because of slow fluctuations. It's slow fluctuations of properties of the condensed matter materials, and I will explain this in a minute. That is in the condensed matter materials of devices that we use, the electronic devices that we use. So, for example, it could correspond to fluctuations in the occupancy of traps in semiconductors, or it could be fluctuations in the location of defects, fluctuations in the location of defects in metals, and so on. Of course, this has been observed in other chemical processes, in the biological processes, and so on. So the list is endless, but this is probably something that's relevant to us. So there is this 1 over F noise. Okay, so to get an idea of this, if you are looking at let's say an op amp, you are looking at the voltage noise density of an op amp. It's typically as we saw before, it's expressed in nanovolt per root hertz as a function of frequency in hertz. So you say 1, 10, 100, 1K, and so on. So this can actually be a significant value. So it goes like it goes down like this, and then it sort of attains a constant value. Okay, so this is what it's typically like in the order of. So this is the 1 over F noise that we are talking about, and typically in the order of it goes down by 3 dB per octave. Okay, the energy is fairly constant across these different octaves. Okay, so that is actually a significant factor in determining where you want to do your detection. If you are doing your detection outside of this, let's say at a frequency of say 10 kilohertz or something greater than that, if you are moving your detection to these type of frequencies, then you can possibly avoid this 1 over F noise, and of course finally you will beat it down through the lock-in detection back to the baseband to do your final to extract your final signal, but you are essentially avoiding a lot of other components through which you can accumulate this 1 over F noise. So you essentially have this 1 over F noise contribution only from from things beyond that mixer as far as your lock-in detection is concerned. So that's actually one of the main reasons why we may want to do lock-in detection, so that you can push your instead of making a static measurement where you send some uniform intensity into your gas cell and make a static measurement, you could actually send modulated light, okay, and then you could actually do this detection, and then of course you can demodulate that light and move our whatever measurement back to the DC and extract our signals. That is, in this case, it's the gas concentration or the intensity that's representative of the gas concentration is what we are picking up. So actually, let me give you an example of this. So let's just take one of the examples that we have considered typically is this OPA 656, right? So, oops. So this is actually the I was trying to get to that particular opening page, but doesn't matter. But this is actually corresponding to OPA 656, and this is actually the voltage noise density for OPA 656, which basically says, okay, the noise density is very high at low frequencies, okay, and then it comes down as you go to higher frequencies, and beyond certain frequencies, in this case it's 10 kilohertz, beyond certain frequencies it's just white noise, okay. So that is what we are talking about. We're looking at it's called pink noise because it's happening at lower frequencies, in the white spectrum, which color consists of blue all the way to red, pink and all that. This is actually it's happening at lower frequency, which corresponds to longer wavelength, right? And so pink is one of the longer wavelengths, so that's why it's called pink noise. Anyway, so you get the idea. So it's to avoid the accumulation of noise at this level that we want to go and do this detection at slightly higher frequencies. Okay, so let me just go back here, and let's actually. So this is where this is the modulation frequency FM that we want to use. Okay, so let us actually move on and say, okay, that is the kind of one example of an amplitude modulated sensor. So let us actually move on to look at another example of an amplitude modulated sensor, and this example is what's popularly known as pulse oximetry. Okay, and this is actually quite popular these days because of the situation that we have with this COVID, and one of the things that it shows up as is breathlessness, and that is actually a condition that's also associated with low levels of oxygen. So there is something called oxygen saturation, which is actually typically the value is anywhere between 0 to 100, but we typically maintain a level of 95, and if it goes down below 90% saturation, then you have a problem. You essentially you have some issue with your breathing, and then that will help that will impact your health as well. Okay, so we want to be able to measure the level of oxygen in your blood. Okay, And we know that oxygen is primarily carried by hemoglobin. Okay, you have what is called oxygenated hemoglobin, which is actually carried oxygen carried by the hemoglobin, and you also have non-oxygenated hemoglobin, which means that the oxygen has already been deposited somewhere, it's been already extracted, so whatever is returning is non-oxygenated hemoglobin. So if you want to look at what's happening in our body, the arteries are the suppliers of oxygenated hemoglobin, right? So they oxygenated blood in general, and so they carry the oxygenated blood, and then they carry to a particular point, and if they have actually been depleted of that oxygen, it comes back through the veins and goes back to our heart, and then interacts with the pulmonary system, and then gets oxygenated again, and then it's pumped out again through the arteries. So that's the kind of system that we have, right? So the blood actually has certain absorption characteristics which you could possibly exploit to understand the level of oxygen that's present in our blood. Okay. So to explain that, let's actually look at the oxygen saturation, what we mean by oxygen saturation in the blood. So if you look at the absorption, of course the blood vessels are within it's within our body, within this tissue and bone and so on. So it's all thin. Yes. So suppose if you are trying to do a measurement of the blood absorption through your finger, then you see that a fairly high level of that absorption or the loss of light could come from just tissues and bones. The bones obstruct the light, and so they don't let it pass. So you get a fairly high level of absorption or losses because of that. And then you have certain absorption due to the venous blood, right? The blood that flows through the veins. The veins are essentially not having or not likely to have oxygenated hemoglobin because the oxygen has already been consumed wherever the blood goes to, the arteries go to. And then on top of this is what you have as absorption of your arterial blood. And that arterial blood again has some constant value, but more importantly it is having certain structure. Don't worry about this exact structure of the waveform, but essentially there is something that's changing with respect to time, right? So most of this is uniform with respect to time, but this arterial blood essentially has a component that changes with respect to time. And how does it change? Well, that corresponds to our pulse rate, right? So whenever our heart is pumping, it's actually pushing blood through the arteries, and that is actually oxygenated blood, right? So this frequency will actually give you the pulse rate. Okay. But what we are interested in is this component here, right, which is a very small component. It's typically only in the order of 1 to 2% of this entire thing, right? So there is a much larger component which is background for our measurement, and we are actually trying to pick up this 1 to 2% modulation, and based on that modulation we can actually tell what is the oxygen saturation. Okay. So, coming back, we are essentially measuring oxygen saturation in blood, and that measurement is through absorption spectroscopy. Okay. So, it is through absorption spectroscopy, but if you try to do absorption spectroscopy, this is what we see. This is the challenge, that we have a very small varying component which we need to pick up, and that is actually quite a bit of challenge. Well, what can we do to make this measurement as precise as possible? You can actually rely on the fact that your absorption as a function of wavelength is actually changing for the blood with oxygen or the oxygenated hemoglobin versus non-oxygenated hemoglobin. Okay. So, we can draw this other plot where we are looking at wavelength, okay, in nanometers, let us say, and we are looking at absorption, but we are looking at absorption of the oxygenated and the non-oxygenated hemoglobin. Okay. So, if you look at the non-oxygenated hemoglobin, that would look something like this, okay, across this wavelength, which could be from 500 nanometers to about say 1000 nanometers. It might look like this. Whereas, if you consider oxygenated hemoglobin, which is typically red in color, that would be something like this. It will flatten out and it will go up, and then it will be something like this. Okay. So, where this happens around a wavelength of 680 nanometers. Okay. And the other wavelength of interest is somewhere around here. It is actually this blue is actually a little flat over here. Okay. So, this is considering a wavelength of about 940 nanometers. Okay. So, if you do sort of a measurement at two different wavelengths, where one wavelength where the non-oxygenated hemoglobin absorbs more, okay. So, that is the red color, okay. And another wavelength where the oxygenated hemoglobin absorbs more. So, this is actually the hemoglobin with oxygen, HbO2, let me call that, and this is actually Hb by itself without oxygen. Okay. So, you are looking at the relative absorption for these two wavelengths, and based on that you are trying to make an estimate of the oxygen saturation. Okay. So, how is it typically done? Well, like I talked about, this is one of the most accessible regions. Some people do it on the ear also, but this is more common. Just your finger, you might have seen there is something like a clip that goes over the finger, and through that they do the measurement. So, what they are actually doing is, so you have your finger like this, let us say this is your nail across your finger, Okay, so you shine because the nail is sort of a transparent region compared to the skin, which is highly absorbing. So you could uh, have these two different diodes. Okay, so one is actually, so you have one diode at 680 nanometers and another diode at 940 nanometers. Okay, and so it's sending out some intensity, and then you need to capture that intensity, which you can do with a photodiode over here. Okay, so what type of photodiode would you use to pick up these wavelengths? Well, if you consider 940, you can actually pick it up using indium gallium arsenide or silicon. But if you consider 680, right, you cannot pick it up with indium gallium arsenide typically. It's got very low responsivity at 680, so you typically use a silicon photodiode. Okay, so now we'll essentially go ahead and design a pulse oximeter, right? So how do you go about designing a pulse oximeter? So you would basically have two LEDs. So these are the LEDs which are driven by a certain current. So why LED? Why not a laser? Well, these features here are relatively broad, that things don't change very much over this region. So an LED is something that's more than enough for these wavelengths, right? So you can basically use LEDs, and so they are emitting this light, and the light is actually going through this through the finger, and then you are able to pick up the intensity that's coming through. So if you talk about the intensity that's coming through, you can just say I of z is going to be equal to I naught e power minus alpha times z, where alpha corresponds to the absorption. But here we understand that absorption is actually a function of wavelength. Not only that, but absorption also consists of multiple components. So alpha is has got one component which is corresponding to non-oxygenated hemoglobin, and another component which corresponds to oxygenated hemoglobin. Okay, so we need to consider both of those, and of course there could be an external loss eta, right? You can essentially take all these losses due to tissues and bones, and you can put that in eta, as well as any other scattering losses from the surface of your nail and so on. So that's an interesting thing, right? So they suggest that you don't put nail polish, because if you put nail polish there, then that can actually mess up these. The nail polish has its own absorption characteristics, and different colors of nail polish has different absorption characteristics that will mess up all these readings. So they typically ask you to remove your nail polish before they make the measurement. Okay. Anyway, so if we were to now look at the actual measurements that we are doing, so let's just call one as one wavelength as lambda 1, another wavelength as lambda 2. So you can write an expression for the intensity at lambda 1. So that will correspond to I naught 1, which corresponds to, once again, the I naught will be the source intensity, right? So I naught 1 corresponds to lambda 1, I naught 2 corresponds to lambda 2, and then you have that external loss factor, which can be a function of wavelength. Okay, so we will come back and look at that, and then you have that exponential term. So you have e power minus alpha hb at lambda 1 plus alpha hb O2 at lambda 1 multiplied by L, where L is the region over which the absorption is happening. That's the corresponding to the thickness of your finger. Okay. So, similarly you can write another expression for lambda 2. So, you have I naught 2 eta 2 e power minus alpha hb at lambda 2 plus alpha hbo2 at lambda 2 multiplied by whole multiplied by L. Okay. So, you are essentially making this measurement. Now, of course, you would say that why don't we use one photodiode for each one of these what do you call light sources corresponding to each one of these light sources and make these measurements simultaneously. If you notice, I have actually shown that there is actually a common photodiode. So, why do I need a common photodiode? It's because of the fact that when you illuminate, so you can maybe focus your illumination in a particular direction also, right. But once it goes into the finger, the tissue, it will tend to diffuse that light in multiple directions. So, if you have two different detectors, it will essentially have a crosstalk with the other detector, not just the detector that it's supposed to go to, but the other detector will also start picking up. Okay. So, one way of removing this crosstalk issue is to turn on only one LED at a time. Okay. So, you basically you go like with respect to, you drive it such that for a certain time one LED is on, for certain other time another LED is on, and then you repeat it. Okay. So, this is basically lambda 1 is turned on during this time, lambda 2 is turned on during this time, and you can essentially repeat it as fast as you can make your measurement itself, right. So, you can switch back and forth, you can switch you can turn on or off one of the LEDs at a time. Okay. So, and of course, during that time you can make this measurement with lambda 1, which is what this measurement is, and then the next time slot you're turning on this LED and you're making a measurement corresponding to this. So, once we have this, we can say if we assume I naught 1 equal to I naught 2, right, then we are and also if we make this assumption that eta 1 equals to eta 2, you have to be very careful in making that assumption, but the wavelengths that we have picked typically justify this assumption, or it could be sort of calibrated out. So, if we assume that is the case, then when we take the ratio R, which is I of lambda 1 divided by I of lambda 2. So, what you have is just the exponential, right. So, you have basically e power minus alpha hb of lambda 1 plus alpha hb of hbo2 at lambda 1 minus alpha hb at lambda 2 minus alpha hbo2 at lambda 2 whole multiplied by L, right. So you just get that factor, and then you can rearrange those terms. Let me see if I can go down a little bit. You can rearrange those terms, and then you can basically get an expression in terms of the measured quantity. So what is measured is actually the ratio, right. So from the measurement you need to infer the oxygen saturation. So you can rearrange it as so this will become minus 1 over L ln of R is going to be given by just alpha HB of lambda 1 minus alpha HB at lambda 2 plus alpha HbO2 at lambda 1 minus alpha HbO2 at lambda 2. Okay. So you once you make this measurement, and if you know what is the level, what are these values of alpha Hb at lambda 1, alpha Hb at lambda 2, and similarly for the other oxygenated hemoglobin, then from this you can actually figure out what is the level of oxygen saturation. So so if it is 0% oxygen saturation, what would these values look like? Well, that would correspond to this case, right. If it is 0% oxygen saturation, then that would, I mean, of course, if you talk about realistic numbers, 0% you're not alive anymore. But anyway, you will see basically these values. So at 680 you will see a value of alpha like this, and at 940 you will see a value like this. So if you see these values, and you will have a corresponding ratio based on that. So you can calibrate with respect to that ratio, and you can say that this would correspond to 0% oxygen saturation, right. So this is 0% oxygen saturation, and on the other hand, if you have 100% oxygen saturation, then you will measure this value, okay, at 680, and you will measure this value at 940. So this will correspond to 100%, okay, and anything in between, you will essentially have some other value over here and some other value over here. So based on that, the ratio is going to change. So you can calibrate all of this. You can calibrate all of this, and then you can say that, okay, this is actually the level of oxygen saturation that you have. And you can clearly see that if you are talking about something like this, you are prone to noise, right. So if you are prone to noise, then this value might fluctuate around something. The intensity will fluctuate around here. So this intensity will also fluctuate, and then correspondingly the ratio will fluctuate, and because of that there will be certain uncertainty in there's a certain level of uncertainty in your measurement, and so that uncertainty in a practical device should not be more than say 1 or 2%, depends on the quality of the device that you have. So you try to keep that as low as possible. Okay, so that's actually pulse oximetry, and that's actually another example of how we can use intensity modulated sensors, optical sensors.